China's fighters are improving fast, but the real shift isn't where most people think it is. For years, one assumption about modern air combat went almost unquestioned. Stealth decides who wins. If you can't be seen, you don't get targeted. And if you don't get targeted, you control the fight. That logic shaped everything. Design decisions, budgets, entire aircraft programs. And for the most part, it worked. But the more I started digging into recent NGAD discussions, the more something didn't quite line up. Not a big contradiction, nothing obvious, just a different set of questions showing up. Less about how invisible these aircraft can be, more about how far they can actually go without support, how long they can stay once they are there, and what they can keep running while doing it. That's a different kind of problem, because stealth gets you in, but it doesn't guarantee you can stay. And once you start looking at it that way, the whole picture shifts a bit. At almost the same time, China reached a point that, honestly, most people expected later. Not a dramatic leap ahead, not something that suddenly beats the US, but enough to change how people are starting to think about it. Because now it's not just about who builds the most advanced system. It's about something harder to see at first glance. So if stealth isn't the thing deciding this anymore, what is? If you listen to how air combat is usually explained, it still sounds like stealth is the final answer. And to be fair, it solved a very real problem. Older aircraft had to fight their way in. Modern ones try not to be seen at all. That shift changed everything, for a while. But here's the part that doesn't get talked about as much. Stealth doesn't remove risk. It delays it. Eventually, you still have to operate inside contested airspace. You still have to stay there long enough to do something meaningful. And that's where things start to get uncomfortable. Because avoiding detection is one thing. Staying in the fight is something else entirely. The more I looked into recent US Air Force discussions around NGAD, the more that distinction kept coming up. Not as a headline, more like a quiet shift in priorities. Less focus on how invisible can we be. More focus on how long can we actually operate once we're there. That sounds like a small change. It's not, because the moment you start thinking that way, a different set of limitations shows up. Range becomes a problem. Endurance becomes a problem. And maybe the most overlooked one, power, suddenly matters a lot more than it used to. Modern fighters aren't just flying anymore. They are running advanced sensors, data fusion systems, electronic warfare suites, and soon, potentially directed energy weapons. All of that requires energy, and not just in short bursts, but continuously. So now the question isn't just how a jet performs in a dogfight. It's whether it can stay, see, and operate longer than everything else around it. And this is where the original assumption starts to crack. Because stealth helps you survive the first part of the mission, but it doesn't guarantee you can finish it. And if that's true, then something else is starting to matter more than stealth. Something that was never really treated as a deciding factor before. And that's the part that leads straight to engines. Once you start looking past stealth, the problem becomes clearer and a bit more uncomfortable. All of those new priorities, range, endurance, power, start pointing back to the same place, the engine. And for a long time, engines came with a built-in compromise that shaped everything around them. You could design for power, or you could design for efficiency, but you couldn't really have both at the same time. That trade-off wasn't theoretical. It directly shaped how missions were planned. If you wanted maximum thrust, you burned more fuel. If you wanted range, you had to accept less performance. There wasn't really a way around it. And most people didn't question that, because it wasn't seen as something you could solve. It was just how jet engines worked. But once you start pushing into longer range operations, especially in the Pacific, that trade-off becomes harder to ignore. Because now you're not just flying out and back. You're operating across massive distances, often without reliable tanker support. And those tankers are becoming more vulnerable, which means fighters can't depend on them the way they used to. So the aircraft itself has to carry more of that burden, more range, more time on station, and more systems running at the same time. And this is where things start to tighten, because the engine isn't just pushing the aircraft forward anymore, it's feeding everything else. Sensors, electronic warfare systems, and cooling systems that stop the entire platform from overheating all depend on it. And if those future programs move forward, directed energy weapons will add even more demand. All of that draws power, not in short bursts, but continuously. So now the question changes. It's no longer just how fast you can go or how hard you can turn. It's how much energy you can produce and sustain while staying in the fight. And if you can't do that, it doesn't really matter how stealthy you are. because eventually you have to leave. And that's the limitation engineers have been working around for decades. Not because they ignored it, but because, until recently, there wasn't a clear way to break it. For decades, that trade-off, power versus efficiency, was treated like a law of nature. You could optimize around it. You could squeeze out small gains, but you couldn't remove it. So missions adapted to the limitation instead of the other way around. You planned around fuel. You planned around tanker availability. You accepted that high performance came with a cost you had to manage. And for a long time, that was good enough. But once the operating environment started to change, longer distances, contested airspace, more systems demanding power, the compromise stopped being manageable. It started becoming the bottleneck. And this is where the US approach takes a turn that, on paper, sounds almost too clean. Instead of choosing between power and efficiency, what if the engine could switch between them? Not before the mission, during it. That's the idea behind adaptive cycle engines. Without getting into the mechanics too early, the concept is straightforward. The engine can redirect airflow depending on what the aircraft needs in that moment. High thrust when you need performance. Higher efficiency when you need range and endurance. Same engine, different behavior. On paper, that sounds like it solves the trade-off entirely. And in testing, the numbers are hard to ignore. Significant gains in fuel efficiency, increased range, and much more thermal capacity to support onboard systems. If that holds up in real-world conditions, it doesn't just improve performance. It changes how missions are designed. Fighters can operate farther from base, stay longer without tanker support, run more demanding systems without hitting thermal limits as quickly. And that's where the implications start to stack. Because once range increases, tanker dependency drops. And once tanker dependency drops, one of the most vulnerable parts of modern air operations becomes less critical. That's not a small improvement. That's a structural shift. But this is also where it gets complicated. Because solving the trade-off on paper is one thing. Making it work reliably, at scale, under real operational conditions, that's something else entirely. Adaptive engines are more complex. They rely on advanced materials, tighter tolerances, and far more demanding thermal management. Which means they introduce new risks while solving an old one. Higher cost, more maintenance complexity, and the possibility that the system works exactly as intended, but only in limited numbers, or only in specific platforms. So while this looks like a breakthrough, and in many ways, it is, it also raises a different kind of question. Not just whether the US can build it, but how widely they can actually deploy it. Because if the most advanced engine exists, but only a small number of aircraft ever get it, then the advantage becomes more limited than it looks at first glance. And that's the part that starts to bring China back into the picture. This is where the comparison starts to get a bit misleading, because it's easy to assume China is chasing the exact same solution. Build an engine that does everything, match or surpass the US, and close the gap completely. But that's not necessarily what they're doing. If you look at how China's engine development has evolved, from reliance on Russian designs to the WS-10, and now the WS-15, the trajectory isn't about leapfrogging every limitation at once. It's about getting to a point where the system is simply good enough, reliable enough to sustain operations, powerful enough to support modern sensors and weapons, and efficient enough to operate at meaningful distances. And that changes the equation in a different way. If the US is solving the trade-off at the high end, with more complexity, more cost, and more risk, China may be solving it by avoiding the need to fully solve it at all. Not by matching adaptive engines, but by building engines that are simpler, easier to produce, and easier to scale across a larger number of aircraft. And that matters, because air power isn't just defined by the best performing platform. It's defined by how many you can deploy, how often you can sustain them, and how reliably they can operate over time. If an engine is slightly less advanced but significantly more available, the trade-off starts to look very different. This is where the WS-15 becomes more interesting. Not because it suddenly outperforms US engines across the board, but because it appears to close enough of the gap to remove China's biggest historical weakness, engine reliability and thrust. For years, that was the limiting factor, with short lifespans, overheating issues, and dependence on foreign components. Now those constraints are starting to ease. And if that's true, then China doesn't need a perfect engine. It needs one that works consistently across enough aircraft to support the kind of operations it's planning, especially in regions where distance still matters, but not in the same way it does for the US. Because China can operate closer to its own infrastructure and support systems, the pressure to solve every efficiency problem inside the engine itself is lower. And that creates an uncomfortable possibility. The US might field the more advanced engine, but China might field more of its aircraft, more consistently, with fewer constraints tied to complexity. If that balance holds, then the competition isn't just about who builds the better engine. It's about who builds the system that can actually be used at scale when it matters. If you zoom out for a second, this isn't really about picking the better engine. It's about what that choice unlocks, or quietly limits, once aircraft are used the way they actually are. An engine sets the terms of the mission. It dictates how far you can push before toning back, how long you can remain effective once you arrive, and how much capability you can keep online without degrading performance. More than anything, it influences how repeatable that mission is over time. That's where the US approach looks compelling. If adaptive engines deliver in service, not just in testing, they don't just add performance, they change operating patterns. Less reliance on tankers, longer persistence inside contested areas, and more headroom for systems that were previously constrained by heat and power. But that advantage only holds if it scales. If complexity drives cost up or availability down, then those benefits concentrate in a smaller slice of the fleet. And that's where the dynamic shifts. China doesn't have to outpace that design. It has to remove the constraints that used to hold it back and then apply that capability consistently across more aircraft. Not flawless performance, reliable output. If that shows up in numbers, the balance moves in a quieter way. Not through a headline breakthrough, but through presence that accumulates. More aircraft ready, more missions flown, more time where it counts. At that point, the earlier assumption starts to fade. Stealth and raw performance still matter, but they don't decide outcomes on their own. What decides it is whether the broader system can support sustained use in real conditions. And that reframes the engine entirely. It's no longer just a component you optimize. It's the factor that sets the ceiling for everything else. So the real question isn't who builds the most advanced design, or who narrows the gap on paper. It's which approach holds up once it's pushed continuously in the real world. Because that's where advantages stop looking impressive and start proving whether they actually last.